What if I told you that trees are not short because they want to be, but because physics won't allow them to grow any taller? Why don't we have trees as tall as mountains? Why doesn't a tree grow 1 kilometer into the sky? After all, nothing is stopping it from the outside. There's sunlight, there's soil, there's space. So what's the limit? The answer is hidden inside water, gravity, and pressure, and it's far more fascinating than you think. Part 1. The dream of a 1 kilometer tree. Imagine standing next to a tree that is 1 kilometer tall. That's taller than most skyscrapers, almost as tall as some mountains. Its top would disappear into the clouds. Sounds powerful. But here's the problem. A tree is not made of steel. It's not concrete. It's alive. And being alive means it has to move water every single second, from the roots all the way to the leaves. Now ask yourself something simple. How do you move water 1 kilometer upward? Without a pump? Part 2. The hidden battle. Moving water upward. Trees don't have hearts. They don't have mechanical pumps. They don't have motors, yet they move water upward against gravity. How? Through something called the cohesion-tension mechanism. Let me simplify that. Imagine a very long straw. You place it in water. You suck from the top. The water rises. Now imagine that straw is 100 meters long. That's already extremely difficult. Now imagine 1,000 meters. It becomes almost impossible. Why? Because gravity is pulling the water down, and water molecules can only hold on to each other so strongly before the column breaks. Trees rely on cohesion, water molecules sticking to each other; adhesion, water sticking to the walls of tiny tubes; transpiration, evaporation from leaves pulling water upward like suction. It's like millions of microscopic straws pulling water up. But there's a limit. Part 3. Gravity is stronger than you think. Gravity doesn't seem strong when you lift a glass of water, but stretch that column of water 100 meters high, and gravity becomes a serious problem. At extreme heights, the water column experiences tension. The pressure becomes negative. Tiny air bubbles can form. This is called cavitation. When cavitation happens, the water column breaks. Once it breaks, water stops rising. If water can't reach the leaves die. If leaves die, the tree dies. So physics puts a ceiling on height. Part 4. What is the actual limit? Scientists estimate that the theoretical maximum height of a tree on Earth is somewhere around 120 to 130 meters. And guess what? The tallest trees on Earth are almost exactly there. The tallest known tree species, the coast redwood, reaches about 115 meters. That's not a coincidence. That's physics. The taller the tree grows, the harder it is to pull water up, the lower the pressure at the top, the greater the risk of collapse in the water column. At some point, it becomes biologically impossible. Part 5. Air pressure also matters. Here's something most people don't realize. Air pressure helps trees. Atmospheric pressure at sea level pushes water upward inside the plant system. But as height increases, the internal pressure drops. The tension increases. The risk of failure grows. If Earth had lower gravity, trees could grow taller. If atmospheric pressure were higher, trees could grow taller. But on our planet, there is a hard ceiling. Part 6. Structural limits. Even if water could somehow reach 1 kilometer, there's another problem. Weight. A 1 kilometer tree would collapse under its own mass. Wood is strong, but not that strong. As height increases, the trunk must become thicker and thicker and thicker. Eventually, most of the tree would be trunk, just to support itself. It would be inefficient. Evolution favors efficiency, not absurd height. Part 7. Energy economics. There's also the question of energy. Leaves need sunlight. Roots need nutrients. The higher you go, the more energy it takes to transport nutrients, the more stress the system experiences. Beyond a certain point, the cost becomes greater than the benefit. Evolution doesn't build giants for decoration. It builds systems that survive.
Part 8. Could trees be taller on another planet? Now here's where it gets interesting. Imagine a planet with lower gravity, higher atmospheric pressure, denser air. On that planet, trees could grow much taller, maybe even several hundred meters. But 1 kilometer? Still unlikely, because fluid physics always imposes limits. Water under tension cannot stretch infinitely. Nature respects physics, always. The aha moment. Trees are not short because they failed to evolve. They are exactly as tall as physics allows them to be. They are engineering masterpieces, operating at the edge of what water can do. The tallest redwoods are not accidents. They are biological skyscrapers built right up to the limit. 1 more meter, and the system risks collapse. That's incredible. Closing reflection. Next time you look at a tall tree, don't just see wood and leaves. See a 100-meter column of water being pulled upward against gravity with no pump, no engine, no electricity. Just physics and evaporation. And realize this. Nature didn't stop at 1 kilometer because it couldn't. And that limit is written in the laws of physics.